Thank you. I will talk about testing graph clusterability. This is joint work with Ashish Chiplankar, Sanjeev Khanna, Aida Muzafifar, and Yuval Perez. Before I proceed, I would like to highlight our junior collaborators, Ashish Chiplankar and Aida Muzafifar, who are around. So this talk is about graph clustering. The problem is, we're given a graph, and we want to partition the vertex set of the graph G into k non-overlapping sets, C1 through Ck, that look like communities or clusters. So for example, for the graph on the slide, a partition into 3 clusters like this, C1, C2, and C3, is a pretty reasonable solution. Clustering is a basic primitive in graph analysis and has numerous applications. So in this talk, we're interested in the following question. Given a graph G, we want to have a very fast algorithm or sublinear time algorithm for testing whether or not this graph admits a clustering with a small number of clusters. So in what follows, I will tell you about the problem that we're solving, namely distinguishing between graphs that are clusterable and that are not clusterable in some sense, and about our techniques. Okay, well first, what does it mean for an induced subgraph to be a good cluster? So here we have a subset of vertices C, or an induced subgraph, and we quantify the notion of a good cluster using inner conductance. So here for this cluster C, we have for every cut S in the cluster, the conductance of S in C is nothing but the number of edges that cross the cut, normalized by the volume of the smaller side of the cut. And note that here the volume is with respect to the degrees in the ambient graph, not the degrees in the induced subgraph. Well, the inner conductance of a cluster is simply the minimum of conductances over all the cuts. And for us, a valid cluster is a vertex-induced subgraph C with inner conductance lower bounded by some parameter phi n. Well, let me mention that the inner conductance of a cluster is related to the eigenvalues of the corresponding normalized Laplacian through Cheever's inequality. And in graphs whose inner conductance is lower bounded by some parameter phi n, random walks mix in at most 1 over phi squared log n time. This will be important for our development. Okay, so now I can tell you what the problem that we're solving is. So we want to distinguish between graphs that are clusterable and that are not clusterable. So what does it mean to be clusterable? We say that a graph G is k phi n clusterable if there exists a partition of the vertex set of the graph into at most k pieces, C1 through Ch, so H is at most k, such that every one of these subgraphs Ci, as induced subgraphs, has inner conductance at least phi n. So here on the slide, for instance, you have an example of a 3-clusterable graph. All right, so these are clusterable graphs. What are the graphs that are not clusterable by our definition? We say that a graph is k phi out unclusterable if the graph G, or if the vertex set, contains k plus 1 pairwise disjoint subsets, C1 through Ck plus 1, such that every single one of these subsets has non-trivial volume, say not much smaller than a 1 over k plus 1 fraction of the entire volume of the graph, and has pretty small outer conductance. So the boundaries are sparse. Outer conductance is at most some parameter phi out. Okay, and here's an example of a 3 unclusterable graph. It's 3 unclusterable because you see 4 disjoint subsets with sparse boundaries. So this is our problem. We call it the partition testing problem. The problem is to distinguish between the yes case, when the input graph is k phi in clusterable, and the no case, when the input graph is k phi out unclusterable. Well, to simplify notation, I would like to substitute phi n equals a constant from now on, and I will call phi out epsilon. So think of epsilon as a small constant. So this is what we want to do. In the yes case, we have a graph that can be partitioned into at most k induced expanders. In the no case, there are at least k plus 1 vertex disjoint pieces with boundaries of sparsity at most epsilon. All right, well, before we distinguish between the two cases, it's a good idea to make sure that they're actually disjoint. And it's not hard to convince oneself that if epsilon is smaller than a constant, then indeed these two classes are disjoint. Because you can't really package up these k plus 1 pieces into only k expanders. Good. So how would one even think of solving such a problem? One natural approach is to try spectral partitioning. Specifically, given a graph G, we want to find k plus 1 subsets with small outer conductance. One very natural approach is to compute the SVD of the normalized Laplacian of our graph, then project the vertices, embed vertices of the graph into Euclidean space using the bottom k eigenvectors, and then partition the corresponding point cloud. So that's a very natural approach, but computing the SVD is quite expensive, especially if your graph is large. So what we would like to do is design a sublinear time algorithm for this problem. We will operate in the standard model for sublinear time algorithms. That is, our algorithm at unit cost can perform the following queries. First, we can get the degree of any vertex at unit cost. And second, for any node u, we can get the jth neighbor of this node for any j at unit cost, assuming this neighbor exists. So this is a standard model for sublinear algorithms and sparse graphs, and it's quite powerful. One can do sampling, one can run various exploration processes, and that's what we're going to do. Okay, so this is our main result. We show that one can distinguish between graphs that are k omega 1 clusterable and graphs that are k comma epsilon unclusterable using time at most n to the 1/2 plus order epsilon times some poly k log n dependence. Now this result is stated for simplicity under the assumption that the graph is sparse. The number of edges is order n, but everything generalized. Okay, well, one thing to note is that the algorithm is sublinear, that is sublinear in n, as long as epsilon, the gap between inner and outer conductances, is smaller than a constant. In particular, this also has strong implications for a property testing version of testing graph clusterability, but I don't have time to talk about this in this talk. It is very useful to compare this result to expansion testing, which is the problem of distinguishing between a graph that is one clusterable, so it's a good expander, and a graph that has at least two clusters with sparse boundaries. So this problem has received a lot of attention in the literature, and one should note that for some version of expansion testing, we know how to solve the problem in roughly square root n time. So the natural question is this dependence on epsilon in our result necessary, or is the algorithm slow? Well, it turns out that the dependence on epsilon is actually needed. Well, we prove that any algorithm that distinguishes between graphs that are one clusterable, so think of a good expander, and graphs that are 1, epsilon unclusterable, think of two expanders with a cutoff sparsity epsilon, must make at least n to the 1/2 plus omega epsilon queries to the graph in this model. Okay, so this is the result. So now let me tell you how we get there. Now, specifically, I will first talk about some prior techniques that have been developed for the problem of testing cluster structure, and then we'll talk about our approach and give some of the main ideas of the analysis. Okay, good. So first, we will assume that our graphs are regular. This is for simplicity, everything generalizes. And we will let M denote the transition matrix of the lazy random walk on our graph. We will choose a parameter t, think of a large constant times log n. This is the length of the random walk that we will run. We'll use random walks. With this notation in place, m to the t times the indicator of u for some vertex u is nothing but the distribution of a t-step random walk started at u. Okay, well, the best prior result on the problem of testing cluster structure is the work of Chumai, Peng, and Zoller from Stock 15. This is a very nice algorithm that works like this. Well, we start by sampling a set S of uniformly random vertices in the graph. The set S has size poly k in the hopes of hitting every cluster at least once with good probability. Once we take the sample, we construct a similarity graph H on the sample. Specifically, for every pair of vertices U that made the sample, consider the distributions of t-step lazy random walks out of U and V. So what Chumai, Peng, and Zoller do is they add an edge between U and V if these two distributions are close in Euclidean metric squared. Specifically, if the Euclidean distance squared between the two distributions is less than, say, 1/10n, then you add an edge, otherwise you don't. And then the graph G is considered, is declared to be k-clusterable if and only if this similarity graph contains at most k-cliques, is a union of at most k-cliques. Great, so when does this work? Well, Chumai and others show that this algorithm works whenever epsilon, the gap between the outer conductances, between conductances in the two cases, is much smaller than 1/log n. Think of much smaller than one of the length of the random walk that you run. And intuitively, this is because in this parameter regime, random walk distributions are pretty good proxies for the spectral embedding that one would use in spectral techniques. And to put this in perspective, it is useful to consider the following simple instance of the problem. Suppose that my graph is actually a union of, say, 3 expanders with sparse boundaries, and I would like to detect this fact. Now, let me choose t to be c log n. This is the length of the random walk. And then for every vertex u, I want to look at the t-step distribution. I want to project this distribution onto the second and third eigenvectors of the normalized Laplacian. And this gives me a point cloud in 2D. So these are the points that are shown on the slide, and you see the 3 clusters. Now, this is a very meaningful thing to do, because if we run the random walk for a logarithmic length, the other components, eigenvectors higher and eigenvectors higher than 3, will just die out, and they don't matter. So because of the outer conductance is so small, under the setting of Schumann and others, smaller than 1 over log n, as you see, after you run the random walk, you get a really good proxy for the spectral embedding. At the same time, in our setting, when epsilon is merely a constant, there is a hefty price to pay for running random walks for a logarithmic length. The embedding that we get becomes a highly distorted version of the actual spectral embedding, and this is what we have to work with. In particular, one can check that in the setting when epsilon is merely a small constant, no distance thresholding method can be made to work. Now, this brings us to what we actually do, so our approach. Well, we also start by sampling a smallish number of vertices from the graph in the hopes of sort of hitting every cluster roughly proportionately. And we run logarithmic length random walks. However, the way we process the data is very different. Specifically, consider the following matrix. This is the matrix m to the t times s, where s is the sampled vertices. Now, this matrix is an n by poly k log n matrix, where the columns correspond to the t-step random walk distributions out of the vertices that we sampled. Now, our main observation in this algorithm is that if the input graph is k clusterable, that is a union of at most k good expanders, can be partitioned into at most k good expanders, then for any choice of sample vertices, u1 through us, the corresponding matrix m to the t times s is really close, inverse polynomially close for a large inverse poly to a rank k matrix. On the other hand, if the input graph is k epsilon unclusterable, meaning that there exist at least k plus 1 vertex disjoint subsets with non-trivial volume and cuts of sparsity epsilon, then with a pretty high probability over the choice of the sampled vertices, the matrix MTS, the matrix of random walk t-step random walk distributions, is far from any rank k matrix, namely has large rank. All right, so how does one test such a condition? Well, a very natural approach is to look at this matrix MT times S and consider the Gram matrix and compute the k plus first eigenvalue. This will tell us whether or not the matrix is close to rank k or not. And this is exactly what we will do. Now, at this point, it's interesting to note that the result of Chumai, Peng, and Zoller can essentially be viewed as the following approach. You still look at the matrix of random walk distributions, but then when you look at the Gram matrix, you round this matrix to 0 or 1, according to a certain threshold. And this turns out to work if epsilon, the sparsity, is much smaller than 1 over log n, the length of your random walks, but it does not work for constant epsilon. All right, so this is finally our algorithm. Again, we sample some set S of vertices uniformly at random in the hopes of hitting every cluster proportionately. Then look at the matrix of t-step random walk distributions and compute the Gram matrix of these distributions approximately. After that, compute the k plus first eigenvalue of this Gram matrix and compare it to a threshold. The threshold turns out to be n to the minus 1 minus epsilon. Our algorithm says that if the k plus first eigenvalue of this Gram matrix is larger than this threshold, then probably the graph was shattered into at least k plus 1 components, and hence it's not k clusterable, we return no. Otherwise, we return yes. Okay, well, one very natural question to ask is, how exactly do we plan to compute this Gram matrix approximately, and why would this even be a sublinear algorithm? Because this is a Gram matrix of n by poly k matrices. Well, What we need to do is approximate this Gram matrix to sufficiently good precision. Specifically, if the threshold for eigenvalues is n to the minus 1 minus epsilon, this is the precision that we need. Well, a moment of contemplation reveals that the a-bth entry of this matrix is nothing but the probability that the eighth sampled vertex, the probability that the t-step distribution from the eighth sampled vertex collides with a t-step random walk from the bth sampled vertex. So we need to understand collision probabilities between two vertices to approximate this matrix. And this can be accomplished by collision counting, basically by the birthday paradox. One can verify that you can approximate this quantity, the dot product between two distributions, to additive precision n to the minus 1 minus epsilon in time roughly n to the 1/2 plus order epsilon. And that's why the algorithm is sublinear time. All right, so let me tell you some of the ideas of the analysis. And first let me tell you about the easy part, which is, let me argue that the algorithm accepts clusterable graphs. Here what we want to prove is that for any choice of the sampled vertices, the distributions of t-step walks are really close to a subspace of dimension most k. And this turns out to be just the subspace spanned by the bottom k eigenvectors of the normalized Laplacian. So for simplicity, let me do the case of k equals 2. So here we have a graph that is 2 clusterable. It's a union, it can be partitioned into 2 good induced expanders. And the question to ask is, how big is the third eigenvalue of the normalized Laplacian in this graph? Well, if there were no cross edges between the two expanders, then we would know that this is just a union of two expanders. The union of the spectrum of a union of two graphs is the union of the spectra. Every expander can only have one small eigenvalue. We have two expanders, so the third eigenvalue of the normalized Laplacian has to be large, omega 1. In reality, we do have cross edges between them, but adding the Laplacian of these edges is a PSD change to the Laplacian of the graph, and hence the third eigenvalue stays large. Okay, well, we're interested in the k plus first eigenvalue of the Gram matrix, but that's 1 minus k plus first eigenvalue of the Laplacian raised to power, which is roughly the length of the random walk, and the length of the random walk was logarithmic, we get a very small number. So whatever the sample, the k plus first eigenvalue of a Gram matrix for clusterable graphs is very small. Good. So that's the easy part of the proof. The challenging part of the analysis is arguing that our algorithm rejects graphs that are not clusterable, unclusterable graphs. So here what we show is that if the input graph is unclusterable, so it has at least k plus 1 largish disjoint components with small boundaries, then the distributions of t-step random walks span a subspace of dimensions strictly bigger than k, in particular k plus 1 and above. To do that, we exhibit a subspace inside the low eigenspace of the normalized Laplacian that only contains fairly flat vectors. And so these vectors are preserved under sampling. So this is the part that only works with high probability over the sampled vertices S. Okay, so this gives us the algorithm, and in the remaining few minutes, let me just say a couple of words about the lower bound. The algorithm that we obtained distinguishes between graphs that are k clusterable and are k epsilon unclusterable using runtime n to the 1/2 plus order epsilon times some poly k poly log n factors. So why is this epsilon needed? Well, we prove a lower bound that shows that it actually is. And the main technical tool behind our lower bound is something that we refer to as the noisy parities problem. In the noisy parities problem, first, nature samples some random constant degree graph, and we use a random deregular expander. This is important for the reduction. And then a uniformly random bipartition of this graph. So now the algorithm doesn't know the graph G and doesn't know the bipartition. The algorithm gets to adaptively query edges of this graph. And upon querying an edge, the algorithm receives the edge with a binary label on the edge called YE. Now the game can be in two cases, either the yes case, the informative case, or the no case. In the yes case, the labels that the algorithm receives tell it whether or not this corresponding edge goes across the bipartition, except sometimes there are errors. So every label is nothing but the XOR of the corresponding bits on the endpoints, plus some noise random variable z, which is Bernoulli epsilon. In the no case, the labels on the edges have nothing to do with the bipartition. Now the algorithm should ultimately distinguish between these two cases. So here's a picture that goes along with this. In the yes case, we have a graph, and there's a bipartition, which is top versus bottom, and most edges that cross the bipartition are labeled blue, Those edges that don't cross the bipartition are labeled red, except there are some mistakes here and there, an epsilon fraction of mistakes. On the right-hand side, there is no correlation between the bipartition and the colors of the edges. So we show that any algorithm that distinguishes between these two cases must make at least n to the 1/2 plus omega epsilon adaptive queries on a random bounded degree graph. And now the intuition for this is very natural. Think of epsilon being 0. If epsilon is 0, then even in the case of epsilon is 0, one cannot really distinguish between the two cases before the algorithm finds at least one cycle in this graph G. But finding a cycle can be easily seen to require at least square root n adaptive probes, and this in fact recovers the square root n lower bounds for testing expansion. Now, if there's some noise on the edges, finding one cycle is not going to help because cycles are pretty long, logarithmic length, and noise adds up over the cycle, so you need to find more of them. And our lower bound makes it formal, so why you need to go for a large number of time. Okay, after that, good. So equipped with this tool, we give a reduction to clustering, and this reduction relies on the fact that you need a constant degree deregular graph. It is interesting to note that the yes and the no cases are switched for our testing clusterability problem and for this lower bound. We also show that a similar lower bound applies to approximating max cut value in sublinear time, but we learned after posting the paper on the archives that this is actually already known due to a very nice work of Yoshida from 2011. Our proofs are completely different, though, and use Fourier analysis, so there should be interesting on its own. So there's also a max cut result. Good. So to summarize, we gave an algorithm that optimally tests cluster structure in graphs in sublinear time. Specifically, we can run in time n to the 1/2 plus epsilon, which is tight up to constant factors on the epsilon. And there are lots of interesting open problems under the general umbrella of doing spectral graph theory or local clustering algorithms in sublinear time. Thank you.
Thank you, Michael. Any questions?
How important is it that you assume that the clusters are expanders?
Okay, if the clusters are not expanders, I'm not sure if you, the yes and the no cases are not even disjoint. Oh, no, wait. So let me say that.
You can ask for a gap.
Oh, no, note that in the yes case, the clusters are expanders. In the no case, there is no such assumption. In the no case, we only want, the only thing we want is that there are k+1 subsets, vertex-induced subgraphs, with sparse boundaries. There are no guarantees on whether or not the induced subgraph is actually an expander, and most of the challenge in the proof comes exactly from this. Because from the no case, it's actually not that easy to understand what the random walk does on the corresponding graph. Yeah, that's good. Yes? Can you repeat, please?
So what prevents us from proving proper testing of clusterability when the number of edges are not linear? In your main theorem, you have an assumption that.
Oh, I see. So good. The question was why can't we have a theorem that does not assume that the number of edges is order n? As I stated there, I only stated the theorem with m equals order n for simplicity. Actually, our theorem applies for any m. And the runtime becomes m to the 1/2 plus order epsilon. So it's like m versus n. I'm pretty sure that you can improve m to the 1/2 plus order epsilon to n to the 1/2 plus order epsilon, but we didn't do this in this work. So yes, the current results actually work for arbitrary densities. You lose something in the runtime, but yeah.
So you already have a result, or it's just a racing?
Oh, no. If you look at the paper says the paper states that there's an algorithm with runtime m, the number of edges, raised to 1/2 plus order epsilon. It's just for simplicity of presentation, I stated it as n to the 1/2 plus order epsilon, because this is really the standard setting. In property testing, it's a little bit easier to understand.
Okay, let's thank speaker again.